Okay, this lesson is about understanding the derivative concept from a graph. So if you remember the last lesson that we looked at, we had a function like g of x equals x squared minus 2. And then we went through some work and found that g prime of x is equal to 2x. So this lesson is all about understanding this connection, but from a graphical point of view. So the first thing I'm going to do is to look at a couple of examples just from a graph. So this is the first one that we're going to take a look at. And you might recognize this graph. This is a pretty common one in mathematics, the absolute value function. So this here, f of x, is equal to the absolute value. So what we're going to do here is to sketch a graph the best we can of f prime. So we're going to sketch the graph of the derivative just based on the graph of the original function. So some things that you can tell right away, this function here is comprised of y equals x on this side, and then on the other side it has y equals negative x. So if you think about the derivative as the slope of the tangent line, or just the slope of the line, you can see this here has a slope of 1, and this has a slope of negative 1. So if you want to graph the derivative here, and make a new set of axes here, we can tell on the right-hand side of 0, the derivative is going to flatline at 1, because the slope of this line is 1. So it's going to look just like this. But on the other side of 0, the slope is minus 1. Okay, the tricky thing about this graph is what is happening at this location. So notice that the tangent line is ill-defined at that location because of the nature of the graph. So we can't really say that the function here has any slope at all. So we indicate that with open circles here, right? So the derivative is not defined when x equals 0, but it's perfectly defined here, right? The slope is 1, and then the slope is minus 1 here. So given this function, if we call this f, right, this down below, this is a graph of f prime. So this graph literally gives you a running tally of the slopes of this graph. Okay, so we're going to take a look at one more here. So the same exact thing that we're going to try to do here. So here is just an arbitrary function. We're going to call this f. And then what we have to do is to sketch f prime. Right, so to sketch the graph of f prime. So what I'm going to do is to put the axes down below in the exact same location. And so we'll have f here and f prime down here. So the couple of the things that you might notice is where the slope is 0. So if we look over at minus 1, for example, if you come up to the graph at this point where the graph has a maximum, you can see the slope of the tangent line is flat, and a similar thing happens here. So what this means is if you were to graph the slope would be 0 at both of these locations. So it appears to be happening at about minus 1 and positive 1. So when you graph f prime down here, we can put a tick mark at minus 1 and a positive 1, and we can fill in these two spots. Okay? Because if the slope is 0 here, what we're trying to do down here is to graph the slope. Okay, so that's what this is all about. So then to look at some other areas, notice on this graph to the right of positive 1, the slope appears to be positive. So if you look anywhere over here, the tangent line might look something like this, or it gets even steeper here. So what we're going to say is if we stay to the right of 1, our graph is going to be somewhere up here, right? It's going to have positive slopes. And a very similar thing to the left of minus 1, if you were to put a tangent to the graph about here, you can again tell that the steepness of that line is positive. So to the left of minus 1, right? We're going to have positive values. The only place where this graph is going to have a negative slope is in between -1 and +1. So if you draw any tangent to the graph in between -1 and +1, the tangent line is falling from left to right. So for example, we can put one right here. And you can see the slope is negative there. So that means in between -1 and +1, our graph is going to live somewhere down there. So a lot of the intimate details have to be taken with a grain of salt, but you can see the rough shape of your graph as it starts above the x-axis, goes below, and then goes back up. So the basic trend that we're seeing here, and this won't be perfect, we have some of the graph here, it lives down here, and then it comes back up. So one way to do a quick check to see if the graph looks pretty reasonable, I would just pick a point. So if you grab a point, say, to the right of 1, so I'm going to grab this location here, and you go up to the graph, and then you find its y value right here. So this is telling us if this is a graph of the derivative, then if you go to the right of 1, the slope is going to be equal to this. And this value appears to be slightly bigger than 1. So if you look at the same location on this graph, so if you go slightly to the right of 1, so I'm going to pick about this point right here marked in green, and then you go down to the graph and find that location, and then draw a tangent line, just like that. So we're saying that the slope of this line, right, is given by the value that we read off the graph right here. So remember, this graph is a graph of the slope, right, and it gives you the values as the derivative changes across the graph. So we have f here, and then the graph of f prime down there. So the last couple of things here, there's one important theorem, and this is one that you'll find in calculus, another if-then statement. So this statement says if the function has a derivative, right, so if f is differentiable at a point, x equals a, then that means the function is continuous at that point. So one way of abbreviating this is you can say that differentiability implies continuity. So this is a local result, just talking about x equals a. So we can express it or abbreviate it this way. So differentiability implies continuity, right? So this is the direction in which it works. So an equivalent way of understanding this is taking the negation of both of these but reversing the direction of the arrow. So you could say if a function is not continuous, then that means it's not going to be differentiable. So we could write it this way. Not continuous, right, implies not differentiable. And one of the big points here of this section is to investigate conditions when this occurs, right? So when we have a function that fails to have a derivative at a point. So this is the question that we're going to ask here, right? So one of the focal points is when is a function not differentiable at a point? So you can see that this question here is directly connected to this conclusion. So to look at one condition, when is a function not differentiable, you can certainly take this condition here. So if the function fails to be continuous, then automatically, right, it's not going to have a derivative at that point. So that's one condition. Another condition that you might recall, when we don't have a derivative, we can look back at this earlier example that we talked about. So here, the absolute value, we know we had the derivative here, and then also here, but the derivative was not defined at this point, mainly because the tangent line as a construct is ill-defined there. So this is telling us that if you see a sharp turn in the graph or just a sharp change in direction, then that's also a case when you're not going to have a derivative. Okay, one more case that we should look at here, because this is a good one that we can just talk about. So this is when the graph gets very, very steep. So I'll try to demonstrate this with a graph. So here's a picture of f. So you'll notice here in certain locations you can definitely sketch the tangent line. So I'll just put one in here. So that's the tangent line there. You can see it has a positive slope. And there are other locations where you can certainly do this, right? You can look at a tangent line there. So the one place where you're going to have a problem is exactly in this location here, where the tangent line becomes infinitely steep. So if we try to, or if we attempt a tangent line right here, right, this is what we call a vertical tangent. So the slope here is infinitely steep. So m here we would say is infinite. Or we could simply say that the slope is not defined there. So anytime that you have a graph that is infinitely steep, that's another case, right, where the function is not differentiable, but only at that point. So otherwise, if you look at this graph, it is perfectly differentiable at the other points. So finally, the last thing here is if you address this question, when is a function not differentiable at a point, you can summarize it by the three conditions that we just talked about right here. So a function is not differentiable if it's not continuous at that point, right? That's certainly a condition. It might have a sharp change in direction or a cusp at that point. And finally, it might have a vertical tangent, just as we saw in the graph.